Thanks, Peter. Thanks to all of you for coming over here. I realize this is supposed to be a talk aimed at a broad audience, and that's what we have here, though I do see a fair number of friends over here. And I do hope you'll find something interesting, nevertheless, in this talk. I'm going to be assuming very little, and I'll be very honest, you'll probably see very little that's new. Nevertheless, I think there is some very interesting notion that we have been sort of both the theories of computer science and the theory of electrical engineering, which has traditionally studied communication, have sort of left in between the two spaces, and there is room for us to expand and cover more questions and themes in this area. So let me jump ahead and try to explain at least some of the ideas that went into this talk that I'm preparing. What do I want to talk about? I want to talk about communication. But throughout this talk, communication refers to digital communication, ideally communicating sort of bits, bytes, data, etc., not analog communication. That's not something that we are that's not our focus today. And the challenge is that communication comes with lots of, objectives. Communication can actually be expensive when you have a satellite going off into space and sending beaming signals back to Earth. It's actually expensive to communicate bits. It can be very noisy, of course, which happens both with the satellite communication setting, or if you're trying to store information, which is like communication over time. I want to store information today and recover it in a year from now. Bits can get flipped. The DVDs that you put the information on can get scratched. And more interesting aspects that we will see later today in this talk is communication is interactive, and when you decide to do things that are interactive, every one of these questions that you're thinking about becomes a little bit more, more challenging. It's more complicated. And a theme that I definitely do want to get to towards the end of the talk is that computers are communicating today, but they're also at the same time computing, and this interaction between the ability to compute versus the need to communicate is always been somehow at odds with each other, and this is something that we want to talk about a little bit. Now, you can ask the question, why talk about a theory? I mean, computers are communicating and they're doing pretty well. Why not just use whatever works? And I do want to emphasize this. This is a talk on theory, but there is a reason why theory is very important in these kinds of settings. So ad hoc solutions work today, but I don't know how well they'll work tomorrow. So this has been a constant problem with methods and solutions that we proposed for all kinds of engineering problems, including the setting of communication, where there's often methods that we can figure out today that will actually work fairly well on the current instances that we're looking at. But when we decide to say, well, and suddenly when you've sort of built the protocol, deployed it, you suddenly realize, oh, there are unexpected problems. Theory typically helps us anticipate and address those things. And formulating a problem, something that I try to teach all my students is, before you give me the solution, tell me what was the problem that you're trying to solve. Okay, this is a very important mantra, and I think it's very, very important that we don't confuse the two. The solution is not the first thing that you should be focusing on. It's the problem itself. And sometimes once you decide that you formulate the problem very carefully, you will find creative solutions which sort of surprise you. You realize it's actually well within the scope of what you were allowed to do, and so you can run with it. And hopefully you'll see some of the effects of these things today. Sorry, something's bothering me. Okay, so, and finally, I mean, when you formulate problems carefully, you can actually understand the limits, and these limits are as important to us as the ability to solve the problems up to a certain point. Why can we not do better, and what are the barriers to solving them better, which might actually just suggest a way to go around the barrier. Understanding of limits is a fundamental question, and these are the reasons why I think theory is important. I'm probably preaching to the masses over here, preaching to the converted folks. So nevertheless, I think it's good to keep these in mind as we figure out So I'm sorry, I'm having a little bit of a problem with the clicker, so I'm going to try and see if I can fix this. All right, so and finally I said, old and new theories. Why new theories? Why the old ones somehow lacking in some aspect? And quite interestingly, I think over here it's a case of not quite that, but exactly the opposite problem. The old ones were so good that we started building systems that were designed with the theory in mind, and they started solving problems. We actually do communicate very effectively with our data today, and as a result we took every piece of every artifact that we were thinking we wanted to store and converted it to data. All our photographs, all the albums that we were thinking about, all music, everything is now a collection of bits, and we are very happy with the theory. But as soon as you start having this kind of a theory, you sort of suddenly realize this new realms of possibilities and all kinds of new challenges emerge. And I'll try to explain to you some of these new challenges that are emerging because the old theories were exceptionally successful. So this is going to be the reason why we'll have, the second half of the talk at all, the new kinds of challenges that are emerging and the kinds of solutions that are possible. As the warning again, this is not going to be a very deeply mathematical talk. There is mathematics underlying a lot of the things that I'm going to be talking about, but I might not be able to tell you much about it. Okay, all right. So let's go ahead and jump in, and I'm seeing the same problem again. So, all right. So, what is this task, challenge of reliable communication? This was a problem that sort of started off in the 1940s, the advent of the digital age, and until now we were really, we were communicating even before, but most of the natural forms of communication were analog signals, and noise was something that we were hoping our brain could filter out on its own. We did not have any active intervention to work on the noise as a problem. But in the 1940s, we started thinking about digital communication, and this leads to sort of very interesting and novel challenges. It's no longer a very continuous mode of interaction. You make one small error in the transmission, and you can get catastrophic changes in the functionality of that message. And naturally, messages and natural languages are not designed to be protected against minor single errors. So we have to do some active work, and this was the challenge that was undertaken by the researchers of that era, and we will try to talk a little bit about that. Okay. So one could say, well, there is some reasonable solution to how to actually resolve this problem. You just repeat every message that we want to send. So if I want to send the message, we are now ready, I repeat every letter of the alphabet 3 times, every letter that I want to send 3 times. And this does work, and after you do some transmission, maybe you get some errors, and these errors might hopefully be distributed kind of nicely, uniformly everywhere, but nevertheless you can do some elementary calculations, and this is the depth of the mathematics that you will see in this talk. As long as the number of repetitions that you're putting in makes larger, as you make it larger and larger and larger, the reliability of the information that you're sending is going to get better. Okay. On the other hand, as the length of the message that you're sending becomes larger and larger, the reliability goes down. There is always a chance that somewhere one of these letters you do see too many errors. Okay. When you put the two of these pieces of reasoning together, you realize that the length, the amount of repetition that you have to put in has to tend to infinity as the length of the message also tends to infinity. So repetition suggests something which I think was actually common belief at the time in the 1940s. I wasn't there then, so you have to take this with a grain of salt, but the rate of repetition means as you have to put in more and more and more repetitions depending on the length of the message that you're transmitting, and so the rate at which you're actually transmitting useful messages is going to 0 as the length of your transmission goes to infinity. And this was possibly the state of the belief at those times, till came this beautiful work of Claude Shannon. This is the first of the and one of the most impressive pieces of theory that has ever been probably built is due to him, and this is his theory of communication. And Shannon said, well, let's look at this problem and abstract it carefully. What's the first thing that you do? You build an architecture of a communication system. So before Alice sends her message, she has an option to somehow encode it. Repetition was a way of encoding it. You sent every symbol twice. Maybe there are other ways. Let's just abstract it completely and just say maybe I will send k bits of information as some n letter sequence. How is this? Am I going to go from k letters to n letters? I don't care. There is some function mathematically which describes this map. That's what I'm going to use. Let me try to figure out what is the best encoding function to use based on the objectives. If you've decided that this is what you're going to do, start with some k letters and send some n letters. In our previous example, n was like 3 times k, and we were not very happy with that. We will try other choices later. There must be a matching decoding function which compresses n letter sequences back to k letter things. And what you want from this is the following expression. If I take some message m and encode it, I transmit it over the channel, it will flip some bits. So let's say it adds some error. Then you decompress it by this decoder. We hope that usually you get back what was sent. Okay. We want this message m to be equal to what was sent with high probability. And if we can achieve this, this is a good encoding and decoding function. Its performance is determined by the ratio k over n. How many symbols did I need to send in order to get k things over? Now, expressed in these terms, the prevalent belief of the 1940s was n is going to be superlinear in k. It's going to grow faster than just some constant multiple of k. Even if the error probability was some fixed number, like say 10% of the bits are getting flipped, you probably have to increase things. But we can now ask the question, that was with repetition, what can you do with other encoding and decoding functions? So what are the best ones? And best is determined in terms of this performance measure, the ratio k over n. What is it that we can get? Assume that we want this error, this probability to be very, very close to 1, sort of just to set that aside. Shannon asked this question and came up with this kind of a very remarkable answer. He said that if every bit, for example, is flipped with some probability p, then the rate goes to this quantity called 1 minus the entropy of p. Entropy has this particular expression. The expression is not important except to say, well, okay, it was a closed form thing. You could calculate it for any choice of p. But he also gave us the matching theorem. This is the best possible. What does this entropy function look like? Let's look at a couple of very simple examples. If the bits are getting flipped with probability 0, I send you a 0, you receive a 0. Send you a 1, you receive a 1. Nothing's getting changed. I don't need to do anything very sophisticated. I just send you the information that I have as it is. No need to do any encoding, no need to do any decoding. You're fine. You should get a rate of 1. Indeed, that's what this theorem promises. If p, on the other hand, is a half, it means I send you a bit which is 0, you're going to get a 0 with probability 1/2, a 1 with probability 1/2. If I send you a 1, you're going to get a 0 with probability 1/2, you're going to get a 1 with probability 1/2. You don't need me standing around sending you bits. You can just simulate these things yourselves. Okay, you're going to get a random coin no matter what I send. So there's obviously no capacity in this channel, and this theorem indeed insists that that's what happens. But what happens in between is even more interesting. Sorry. What's even more interesting is that this rate that we are seeing is going monotone, decreasing from 0 to 1/2. What happens beyond 1/2 is not very interesting. Let's go up to this point. But even if the probability of a bit being flipped is like 0.499, it's very, very, very close to 1/2. This theorem is saying that there is a positive capacity in this channel. You can actually use it to transmit information, and indeed actually people think about settings maybe not as close to 0 as on this setting, but in engineering applications we'd probably think about settings where p is close to 0.49 as you send off this satellite into space with extremely weak batteries, so its signals that it's sending back are extremely weak. Or in a more interesting experiment, people were trying to communicate, this is just amateur radio enthusiasts who decided to send signals across the earth by bouncing it off the moon. So they send a signal over from earth, it goes, hits the moon and bounces back. So from New York to Tokyo you send some signals this way and it actually works. You can actually recover information. That's all possible because of these extreme choices of these parameters. Even when p is extremely high, you have positive rate of information transmission. And the most important thing, the rate is linear in n. So it's a very creative solution, not what we were expecting at all, completely contradictory to the belief at the time. And it has the other aspect that I think a theory should really help us with, which is it tells us what are the limits. This is the limit of information transmission. You cannot do any better. So this was Shannon's wonderful theory, and I think so I do want to sort of talk about some of the main contributions. I think the very architecture itself was a contribution. So the fact that you decided to put in an encoder and a decoder, why is it so radical as a thought? Well, we are thinking about very complicated functions that we are going to build into this architecture of an engineering system. When the ability to compute was 0, we had no computers at the time and not much hope that you could implement many of these very, very complicated functions that we were thinking about. And yet you ask the question, okay, but suppose I was able to do it, what would my limits be? So somehow this was a very surprising, strikingly different approach to the problem, and that led us to a beautiful theory which eventually led all the practitioners to chase the theory and eventually get to the limits that it promised. There's a profound analysis, maybe almost an independent discovery of the probabilistic method. It's not enough to say whether this was actually true or not. There's these deep mathematical concepts, notions of entropy, mutual information, etc., which give mathematical meaning to objects which are very intuitive to us, but turn out to be actually, concepts that you can grasp with your mathematical tools and analyze. And even though the initial theory was highly non-constructive, I would say from the 50s to now, it has become very constructive, very algorithmic, really, really beautiful. And the amazing thing about this paper, that Shannon wrote in 1948, it was not just that he was thinking about communication as an engineering challenge, but really as a central challenge in the sciences. He really wanted to understand much more than just how to build the next better magnetic storage medium or an information transmission mechanism. And here is, for example, an aside in the paper which says, well, by the way, along the lines of this, I can actually build a series of approximations to a language like English. And the ith order approximation is built along the following way. If I give you the first I-1 symbols, I tell you what is the probability based on just empirical analysis of the ith letter being some particular letter of the alphabet. And built on this model, he said, okay, let's see how it functions for English. This is a very non-trivial challenge. In 1948, he did not have a random number generator. I just told you he did not have a computer, and he still actually gave us approximations. So this is a order 3 approximation from his paper. Pretty interesting. I mean, this word demonstrators is not in English yet, but and then it gets even better. He decided, well, letters are not taking me very far very quickly, but maybe I can build word approximations, and this is just a second order word approximation. Given any particular pair of words, it's sort of, there's a probability mass on the third word, and you generate things according to this thing, and it starts to look pretty interesting. And even more interesting is, okay, we say, okay, all of this, but does it have any predictive power? And what Shannon actually observed about this, which is pretty interesting, was that somehow I thought approximation produces plausible sequences of length about 2i, which is some statement about English, right? It is not something that I can either prove or in any formal way, but there is something non-trivial. It's a statement about some restrictions of English in some empirical sense. So came up with all of this in just this one beautiful paper. So this is a wonderful paper. I could go on for hours about this thing, but what I want to do today in this talk is really talk about the modern theories. Okay, this was a great opening to the theory of communication. This is what our current internet, cell phone communications, storage media and their architectures are all designed around, and yet there is the next generation of problems which are now we are encountering because the first generation was so successful. Communication tends to be interactive, so I could be, the two of us could be sharing a file somewhere and we are doing some changes simultaneously. I send a thing saying this section can now be deleted, and you think this section cannot be deleted. Maybe that's actually a good way for things to happen. Maybe I could have said this section can I said this section can not be deleted, you interpret it as it could now be deleted, and then you can make catastrophic changes. All the changes that you do afterwards would be errors in our dealing with the file, and it's not errors charged to the computational, to the medium of communication. It's just because of one error at the initial stage of our interaction. So interaction leads to major challenges, and we'll see how and when to correct errors. And there's a collection of other things that I will talk about a little bit more as we go along. So it is actually remarkable, from 1948 till 92, we really didn't think too hard about this question, what happens with interaction? And it was a remarkable piece of work. Schulman, as part of his PhD thesis, I believe, considered this question. So how are we going to actually start doing, correcting for errors in an interactive setting? So here, for example, like in my example, we have Alice and Bob interacting with a server, and a typical interaction is of the form: server tells the user this is what the current document is. The user tells the server, okay, delete these characters, insert these other characters, and so on. And if two of us are acting on this simultaneously, we certainly don't want to have errors which go uncorrected. On the other hand, when do you decide to correct errors? If you decide to look at the first few symbols, notice something is going wrong, what do you change it to? It could be that the minority of symbols that seem to be in error are actually in error. It could be a majority are in error. Maybe you haven't seen enough. This was sort of a bad beginning, but afterwards this channel is going to stabilize. If you decide that you're going to change in favor of one direction now, the entire interaction afterwards is going to assume that the first few symbols are the following. If you decide to do something else, the entire interaction might look completely different. Which one of these interactions should we even engage in if you're not able to tell how to correct, so there's always a challenge. Should we correct errors immediately? Why don't we wait for a long time? But if we wait for a long time, maybe we're doing the wrong interaction all along. So maybe I'll notice that there was an error in the first couple of bits which should have been fixed. I didn't do it, and as a result, I'm now going to have the penalty of saying rewinding all this later interaction that we did, which was completely futile. We should have been going and doing something else. So this is a very fundamental challenge, and even given the state of Shannon's theory, it wasn't clear how well we will be able to address this thing. A concrete question that you could ask over here is again the same thing. If bits that we are sending back and forth between the user and the server, etc., are flipped with some probability p, what is the rate of communication? And once again, I think prior to Schulman's work, it was fairly clear to us that, look, okay, if you're interacting, then rate of communication is not going to be linear. It's going to go to 0 as the length of the communication goes to infinity. And once again, Schulman proved us wrong, and the limits are not as well understood as in the other case. But roughly what we have is that we can actually still do very good communication at a linear rate as long as the probability of a bit being flipped is at most 1/8. And the scaling is no longer 1 minus the entropy of P. Something very different is happening here. It's more like 1 minus the square root of the entropy of P. So something is different. It's not quite clear what, and there are limits over here and upper bounds and lower bounds. These are some of the main folks associated with this theory. There was work by Schulman in 92, and then for a long time nothing really moved, and then in the 2000s till even the last couple of years we've had a whole series of results which have largely clarified this picture for us. So the moral of this story is, even when you are interacting and your bits are getting flipped, and much of this theory holds even if the bits are not getting flipped by some random process. It could be by a very malicious adversary who actually knows what you're planning to do to correct it. You can still correct this fraction of errors, and you might be executing a protocol which is interacting by sending 1 bit each time. All that is okay. We can still actually deal with a large fraction of errors. Okay. So very, very pretty, amazing, and very surprising. I would say very surprising, even given Shannon theory. Obviously, if you just keep sort of reinventing Shannon surprise, everything that I say is going to be surprising. But I'd say this was quite a and the mathematics that goes into it is very, very elegant, very novel. You really had to. Schulman definitely sort of built out a very striking theory, as did Braverman and Rao, and so on. All right, so now moving on back to my challenge with the modern theory. So interaction was an element. We deal with it. I'm going to sort of rewind time a little bit and then go back forward in time a little bit. And interaction has another very intriguing element. Very often we have large amounts of inputs on both the sender and the receiver, and what we care about is some joint functionality of the two. Imagine you're going out to a travel agent. This could be an online travel agent, and you're trying to figure out what tickets you could buy. You have this challenge of saying, should I tell them all my constraints? And this could happen with any online shopping experience. Should you tell them all your constraints and your preferences, or should the other side come back to you with all their catalog of options that are available? Is there something in between where neither of us actually is sending, doing a core dump of all the information? And by the way, till about 20 years ago, we lived in one of the two worlds. Mostly with the travel agent, we would just go up to a person and tell them everything we want. They wouldn't tell us all the flights that exist. On the other hand, with most online shopping, they would just send us a catalog of everything that they have to sell, and we would just read the whole thing and figure out what subset we may be interested in. Clearly, there should be something better that's possible. There's something that's a joint, takes into account the fact that I might not be interested in everything, and you may not have to tell me everything that you know. So how well should we model this? How should we model this, and how can we improve the efficiency of this? Turns out that there is a beautiful theory due to Yao which started to deal with these kinds of questions. So in this theory, Alice and Bob have some private information. In this case, Alice might be the person who's wanting to buy a ticket. X somehow represents all the kinds of preferences and constraints that she has, where she wants to go, what kind of price she's willing to afford, etc., times and dates. And Bob might be the travel agent who knows about all the airlines and all the information related to that. F of x might say, give me a ticket which is satisfactory to me, to Alice. And in this model, what Alice and Bob do is engage in some interaction and eventually produce the value of the function that you're interested in. And the hope is that there is some mechanism for communication which is lot more succinct than sending all of x, sending all of y, and nevertheless achieving this function value. And what we would like to understand is, what is the best protocol? What is the number of bits that we really need to exchange in order to be able to always compute f of x, y? It's a beautiful, very simple model. Very remarkably, this has always been a model for proving lower bounds. We usually come to this model, and page 2 is these are the things that you cannot do other than by exchanging x or y. In this talk, I really want you to change perspective and think of this as a positive model. There are probably games where we can do a lot better, and I'll probably try to give you at least one example of that. Now, you can amplify this model, have some shared randomness. It leads to a lot of mathematical elegance to the theory, but it also turns out to have fair amount of practical significance. Quite often, this randomness can be sort of, dealt with some assumptions on the inputs and so on. I won't exactly go into the details of that, but in general, whenever you allow Alice and Bob to use some common randomness, we will say, okay, as long as they manage to produce the correct value of the function with high probability over purely the randomness, this is a good solution. Okay. Now, as I said, it's usually studied for lower bounds, but I want to think of it as a positive model. So here are some examples of some very simple functions, and I just want to, try to come up with the simplest looking functions for which you could actually come up with non-trivial protocols over here. Here's something that you can do. Alice might have some n numbers, think of them as real numbers, x1 to xn. Bob has some n numbers, y1 to yn. They want to know this sum of the differences. Now, this is obviously a trivial problem to solve. You don't need to exchange n pieces of information in order to solve this problem. I can use some laws of arithmetic, I don't know what they're called, and Alice can send to Bob the sum of all the xi's, and Bob can just subtract the sum of all the yi's from the information that Alice sent him, and that gives us the protocol. 2 rounds of communication, very simple, not n bits of information, so something much smaller. So, really think of this as constant communication. Okay. So this was trivial. This is also, probably much too simple, cannot possibly be modeling very many interesting scenarios, but let's see how we can build some changes. Now, suppose instead of computing the sum of the xi's minus yi's, I want to sum up the squares of xi's minus yi's. Okay. Already the problem looks slightly different, and in fact it is different. You can actually show that this actually requires n bits of communication no matter what you do. So it looks like it's hopeless, but this is why randomness is such a crucial resource in communication. If the players are allowed to do things in a randomized fashion, then they have a very elegant protocol. So suppose Alice and Bob actually shared n random bits, which I think of as numbers either +1 or -1. Alice should compute the following 2 terms, s1 and s2. S1 is just the sum of the squares of the xi's, and S2 is a linear combination of the xi's whose coefficients are given by the R1 to Rn. Okay. Bob can compute an exactly symmetric term, and suppose they exchange S1, S2 and T1, T2. So each one is sending each other 2 real numbers, and you can do some finite precision arithmetic to reduce this thing. It turns out, and trust me, if you evaluate the following expression, S1 plus T1 minus twice S2 T2, this expression is of course dependent on what R1 to Rn are, but if you take the expectation over R sub i's, you get exactly the quantity that you want. So you just try out a few different values of R1 to Rn, you get the a value which is sort of starting to concentrate around this sum of the squares, and you've exchanged it. So the amount of communication goes down to a constant independent of n, and you are now, again, this of course relies on the fact that Alice and Bob share some randomness, but this is a pretty reasonable setting in many, many cases. This, by the way, is a protocol which is roughly due to, I think, Alon, Matthias, and Segedi. It actually pops up a lot in various streaming algorithms and other such, sketching and so on. I'm interpreting it as a communication complexity result, which is really what it is truly. All right, so going back, I'm not going to oversell the application, but really, is this particularly interesting? I think knowing in approximating the distance between points in n-dimensional spaces is a fundamental question in the space of large data. And indeed, I mean, one could easily imagine that I could express my preferences as a real vector. The travel agent wants to express their preferences as their options as real vectors, and we really probably want to say what's the closest match to my preferences that I have over there. This is not going to, I mean, right now I don't know how to do this for the travel agents thing, but in general this is a kind of a paradigm that we've been thinking about a lot. And what this is saying is that, you know, okay, these vectors might be huge, and this n might be exceptionally long for us to be able to make sense of it, but it doesn't enter into the communication. The communication complexity is roughly twice as large as the final itinerary, something that I can live with. Okay, so imagine the kinds of savings that this is promising if you can implement these kinds of protocols. And it's not there yet, we are not there yet, but I think we will get to the point where every one of us will have an assistant in our phone which is able to take all our complicated preferences expressed in English, convert it to vectors. This is where we are going anyway, and we will start being able to use solutions that look like this. Okay. All right, so the drift that I'm trying to get towards over here is in the presence of interaction, there is new kinds of challenges and new kinds of efficiencies that are possible. On the one hand, errors become much more important to deal with and deal with early, but at the same time there is a challenge. You can never ever deal with errors too early. All the errors may be bunched up towards the beginning. And there is also the options that it's offering. Because we are doing things interactively, there may be very creative ways of saving on communication. Me sending everything I know to you is not the only mode by which you and I can interact, and this is something that we certainly practice on a day-to-day basis. Now, a new kinds of challenge is emerging to me, which is related to the concept that, you know, yes, interacting a lot of interaction happens because the two endpoints are capable of computing. But if the two endpoints are capable of computing, they're also capable of reprogramming themselves. So now there comes a challenge. I'm allowed to reprogram myself except when it comes to communicating, because when I'm communicating, I better have a protocol that I'm sharing with you in common, or else the meanings of our bits are lost. Or maybe there is a different way of communicating in which I allow my reprogramming also to have some way by which I can, you know, learn how to speak to you. So the Shannon theory typically works in the original model. You and I will fix a communication protocol and never try to work with this, never try to interfere with that. The communication modules are always fixed, and I can think about every other piece of computation that I'm doing on the side. Where human communication, this boundary is very soft, and we often end up with protocols which, you know, trying to learn to speak by speaking. What is the meaning of a word? If I don't know, I can ask you. So I want to think about problems that arise in the interface between the two, and we'll try to talk about these two issues. One, which is, can we learn to communicate by communicating? And the second, which is, you and I, when we are communicating, we are often assuming a large amount of common context, like, for example, knowledge of English, some knowledge of mathematics. I at least did some probability calculations with you. All of these things, can I really assume? Can I write down what I assumed? Or would it even be feasible for me to write down what I assumed and expect a perfect intersection with you? So these are kinds of questions that intrigue me a lot, and we've been working on it a little bit, and let me tell you a little bit about it. I'll skip this slide because I said the things that I wanted to talk. So in some work that I did with Brendan Juba, who's here in the audience, and so on, we started talking about this question: can we learn to communicate by communicating? You know, how do children learn languages? Well, they do it by communicating. They're not doing it, I mean, there is some debate as to how much of language might be hardwired into the brain, but certainly it's not as much as, you know, the exact, the dictionaries are definitely not hardwired in. And computers don't seem to be ever communicating along those lines. They always have this mode by which they say, at least for today, for the next month, the mechanism by which, say, my text messaging will work will be the following very rigid protocol. In a month, maybe I update it, but I'll update it with everybody does it, and then we are again working in synchrony and so on. So, a nice alternate model would be where we actually use the intelligence at the endpoints to, rather than saying let's suppress it, learn to communicate according to what the third party who built the communication platform told you to do. Let's learn to communicate by interacting with each other. And is there a model which supports this? Can we actually do this? So with Brendan and Odette Goldreich, we asked this question and eventually came up with a theorem which says basically that you can actually learn to communicate provided the communication is sort of verifiably useful. So this turned out to be, how to define verifiably useful was perhaps much of what this paper was about. The theorem was nailed down as the endpoint, and we said, okay, whatever definitions allow us to get here is what we will be happy with. But it also sort of sends us a very interesting message which can be actually made formally and precise mathematically. Communication has to be useful. If it's not useful, there is no reason why I would be able to learn to communicate with you. There's also no reason to be wanting to communicate with you. It better be somewhat useful to me. Likewise, you shouldn't be coming to this talk unless you're hoping to learn something from this talk. So if it is verifiably useful, if I just give you a sequence of random numbers and say these are beautiful random numbers, it's not useful to you because you cannot verify the claim. If it is a claim that you can actually verify on your own, then you can actually interact to learn to get useful information from me. It may not be that we actually are in synchrony in terms of understanding each other perfectly, but it will be that we are in synchrony in the sense that you are able to extract useful information from me, which is a very functional way of achieving useful utility in communication. So this is something that we are able to prove as a theorem. I will not dwell on the details of this, of the definitions over here. Another issue that we try to deal with in later works is computational devices are constantly correcting context information, and this context actually affects communication. So for instance, my phone, in order to be able to do a search on Chrome, wants the ability to do all of these other things which I didn't realize had anything to do with using a browser. Okay, but it needs to, for instance, pair with my Bluetooth device. It needs to know how to control the vibration on my phone, etc., etc. So why is it gathering all this context and incorporating it into a simple, browser functionality? This kind of behavior might be surprising to us and maybe actually not always the right solution, but it is universal in communication. Certainly in humans, you cannot possibly chop off the brain into distinct portions and say these are the parts that are aimed at hearing and this is the part that's aimed at speaking, and they'll have nothing to do with each other. We do not work that way, and that's not how we expect things to work. So context has some very nice pros. Actually, shared context between a sender and a receiver makes communication very effective and efficient. On the other hand, it also brings up new challenges. If you have imperfections of sharing of the context, this is going to make it hard for you to understand what I'm saying. So shared context made today's lecture possible. If you didn't know English, I cannot give this lecture at all. On the other hand, there is imperfection in the sharing of this context. I don't know exactly what subset of English you know, and I can't write it down. And it may not be the same for all of you, yet it works. So what are mechanisms that we can extract in communication that somehow have these two kinds of features that you can analyze this? So we try to understand these things in some work, and this is a theme of work that I call communication with uncertainty. And the two essential elements that we think about over here are context should make communication efficient. On the other hand, there should be robust protocols which allow this context to be shared imperfectly. There's a whole lot of works that I could talk about for another hour. which I don't have, but let me just sort of tell you at least what kind of a model could you use to study some such questions. And it turns out we just go back to the Yao model of communication complexity. Here is a very perfectly nice model in which you can establish these questions. You have some function f that you want to communicate. Takes a lot of communication to compute this thing, but maybe when I throw in the context, communication becomes much more efficient. What could context be? Anything that I didn't explicitly mention as an input to Alice or Bob is context, including things that I've mentioned over here. Maybe the function that is being computed, maybe the randomness that they are using, maybe the distributions of x and y, maybe this was part of the assumptions, maybe other things that I didn't think about but should be, enable efficient communication. And when you take these contexts, communication becomes a lot more effective. But we would like protocols where if these contexts are not exactly matching, FA is not the same as FB, RA is not the same as RB, or the probability distributions that they are thinking about are not the same, but close, in some measure of closeness, you get a little bit more communication but not everything back. This is the kinds of problems that we would like to be able to understand and analyze. There is a lot of work with a lot of people where we talk about a whole bunch of such problems and try to talk about, maybe you don't need common knowledge of the distribution in order to compress information. Maybe in human language and communication we see that the dictionary is a central element, but does it have to be designed centrally and exported to all the users, or could we somehow be evolving in a dictionary on our own? Yes, it can be designed in a distributed manner and lead to efficient communication nevertheless. Things along the lines of, does the randomness have to be perfectly shared? Does the function being computed have to be perfectly shared? Turns out none of these is actually essential, and there are ways around it. So these are some sample results. It's a sporadic collection of results, not yet a theory, I think, but it also points to the possibility of a theory. Contextual communication and communication with uncertain context seems to be a very interesting theme in theory, in communication, and I think is worthy of studying. So to conclude, I think we saw a sampler of some theories of communication. These have been extremely valuable in the technology and in the engineering side, and in addition to being exceptionally practical and useful, it's also, I think the underlying mathematics has been exceptionally pretty. There were many surprises, especially in the early stages, but there is still a big divergence between this theory of designed communication, where sender and user are jointly programmed to be able to communicate, versus the theory of emergent communication, which is what we see with humans, but also increasingly I think devices are going to be practicing this. And can we use some of this theory also to go back and talk about human communication, just the way Shannon did with this model of language and so on? Is there interesting phenomena to be explored and exploited over there? Okay. So that's what I have to say. Thank you very much. Okay. Great, thanks, Anant. So I don't know if everybody could hear the question. The question was, we saw this beautiful theory of interactive communication. Is it ever being practiced somewhere? And the answer, as far as I know, in practice, no. And why? It's conceivable, it could be due to one of two reasons. There is no inherent reason why interaction should be able to help us a lot. Anything that we might want to do can be done in maybe 2 rounds or 3 rounds. Certainly the theory of computing tells us otherwise, but we don't see these very many interactive protocols in practice in general. A second reason might be that we were so fearful of the errors that we decided to make all our protocols minimally interactive. And once you see that you can do a lot more, maybe we will do things differently. So certainly I don't see us engaging with the user server distributed edit model in this frequent things. Certainly when I'm editing a paper with a collection of my collaborators, I tell them, look, I'm going to be editing, you better hold off. Let me finish all my edits and then you start. This is somehow hampering my ability to do interactive communication with the full scope of possibilities. But on the other hand, I don't know that we would go to the extreme of saying, let me allow rapid interaction and take a chance that the system is going to preserve the file, especially since most of the papers are written one day before the deadline. Yeah, so and you said that, does that do what? Oh, absolutely. So when we spoke about the encoding process and the decoding process, the interim process is what we call error correction. Traditionally, I would think of anything that we do to somehow cope with errors an error correction process, and it may range from something as simple as expanding a sequence and repeating it 10 times, something more sophisticated, or in the interactive setting something a lot more elaborate. I tend to believe, or even the contextual setting, anything that I do to say, let me see what you might know and how to incorporate that, I would call that error correction. There are not very many, the theory there is not as well established. Okay. Thank you very much.